Well, also this is not the first time you guys have watched me completely mess up at using technology. Probably won't be the last. So I'd say that's good news, but really it's more just a comedy of errors at this point. Quality of video I was able to produce in the video that I did put out on Tuesday, not one that I could reproduce unless I got some kind of a capture card, and quite frankly, I don't have a capture card, although I am considering purchasing one because then it would give me the ability to use a better camera, which would make this whole thing a lot nicer. So, how do I get the link to this thing? Dang it. If I knew how to get the link to this thing, I could send it out to everybody and we could go ahead and start. But I am not dabbing, Walker. Who created a dab emoji? That's gross. Although thank you for coming and dabbing on my stream. Does anybody know where I'm going to find the link to how to send this out to everybody? Anybody know? I can't. Okay, I'm going to try quitting and retrying this. So, I know this is frustrating. I'm sorry. Nope, I got it. Cool, let me post this to Blackboard real quick. This has been an absolutely fun endeavor in trying to learn how to teach online. So, yes, I am covering one of the most advanced topics we've talked about so far in this class today. And yes, as of right now, I am trying to make technology work while about to teach the hardest topic we've talked about today. So, that's not fun or anything. Okay, I did see that. Thank you. Also, thank you for communicating with me, Walker. This is the essence of what I would hope this would be. Okay, I should have just sent an email out to everybody with the link to the stream. Nobody's liked this video yet, so I hate all of you too. Although this is a really poor quality video, I wouldn't like it. Okay, hi, this is my first. Here. Oh, you can actually see the top of the board. Nope, not quite. Oh, I almost have the entire whiteboard. Nice. Okay. So if you can't see what I'm writing, oh no. Oh, I blame the buffering on the fact that Dome's internet is even better than my internet at home, though. So I guess that's a scathing indictment of the state of internet in Nebraska. Woo! Okay, so last time we talked about AC circuits. And the difference between an AC circuit and a DC circuit is that AC circuits have oscillating power supply. Okay. Usually it's given as some kind of sine or cosine curve. We can draw it like a cosine curve like this, where the function is something like V AC is equal to the equation for a power supply that would come out of, say, your wall outlet, something like that. So, let me make sure that I'm seeing comments. Okay, we're good. Awesome. I'm not gonna cry after this stream is done as much. Also, that means I now officially have my first like on a YouTube stream. So, this is a monumental occasion. Let's celebrate it with pie. I destroyed that pie. Okay, so we now have an oscillating power supply, and that does change the dynamic of how the different components work. The thing about components in an electrical circuit is that not only do we have resistors, which have just a linear relationship, but now we also have the capacitors, which the relationship between derivative relationship, and then we have inductors where the relationship between voltage and current. Now the current is an integral of the voltage. So it does cause issues with this because it causes a delay. And this is where we bring up the idea of what is a phasor. Okay. So now this is incredibly complex. What I did last year's class was I did not assign any homework over phasors because it was really complex and I didn't want to get bogged down with it. And we're teaching this assignment online, and it's really complex, and I don't want you to get bogged down with it. So we're only going to be discussing AC circuits as much as I'm not going to give you any homework over that. Not even a reading assignment. I mean, if you really wanted to go in and read and say, hey, I like to know more about AC circuits, go ahead. I think the textbook does a really good job of laying it out. I'm going to try to, basically the purpose of this lecture is to just give you a foundation of if you run your second test. That will be a big part of your final project. Digital circuits are a little bit more complex, but at the same time, a lot easier to calculate. So we're in a good place there. All right, so we've got AC signals, and we're going to bring up the idea of what is an impedance, okay? An impedance in an AC circuit, what if my camera quality is good enough that you can actually read these words? Huh, I can read it, although it appears everything is backwards. Oh no. I'm going to have to write all of my words backwards. Oh no. Oh, okay, it's not showing it backwards. Thank you, Danielle. Okay, that's good news, because I've never done a live stream before. Why is it showing it up backwards for me? Oh, in an AC circuit, what you have is an impedance is an effective, what is impeding the flow of current, okay? I'm going to use the word hindrances here, so I'm not using. And basically, what prevents current from flowing? In a DC circuit, we can take a resistor and we can say, well, higher resistances make makes the current go smaller. So if I have a DC circuit where I say, here's a resistor, and I take R, and if I increase R, then the current in the circuit goes down. Okay? In a DC circuit, if I wanted to reduce the current, I would increase the resistance. Well, in an AC circuit, what we see is, well, okay, before we get there, if I were to just AC circuit, what we see is, well, okay, before we get there, if I were to just do this, the moment that I plug in a capacitor into this circuit, I have an infinite current, just because it charges this almost immediately. There's a reason why we can't actually create a circuit that looks like this. Every circuit will have some amount of resistance in a wire that prevents this from actually being an infinite current, which means as soon as you plug this in there, all of the voltage across that comes out of the battery is actually going through the wires. It doesn't accumulate, so it doesn't generate a ton of heat. But in this respect, in smaller wires, it may be enough to cause them to melt. Just be careful trying to plug in a giant beefy capacitor into a beefy power source with really tiny lines, because in theory there's no current, but in reality there's always going to be current. But in any case, plugging this in, there is no impedance whatsoever to current flow in this circuit. But if we were to change this to an AC source, there is impedance now to this, the flow of current. What we have is that there's, if we apply VAC, and we're going to model this as a cosine, if we were to apply VAC, and we look at IA, measuring what is the current, well, current for this is not the derivative, it's a derivative of this multiplied by the C value. We do have this relationship that goes on. This is now not going to be a near infinite current. There is some resistance, there is some finite value to what the current is based on the properties of the capacitor. And this is a unique trait that we only see in AC circuits. We do not see in DC circuits for capacitors. Now, if we were to plug in a resistance here, and I were to keep the voltage the same, and you can kind of see, I'm kind of drawing off the edge here. Let me bring this in a little closer. I just need a better camera, or just need to get a capture card. So let's say we've got here an AC source with a resistance. Okay. Here is my VAC. It'll be a cosine curve. There's one full curve. And here's my IAC. This is going to be for a resistor, these two are going to be in parallel. So if this is, let's say this is 10 volts AC, and let's say this resistance is 100 ohms. Okay, then according to Ohm's law, V equals IR, and then we have V, we have 10 volts across the resistor, so 10 equals I, we don't know what it is, times R is 100, which means that I is equal to 0.1 amps. Make that into an I, it doesn't look like my 1. So we know that the maximum value of I here is going to be 0.1 amps, okay? And this is going to have the same time form because the relationship between voltage and current is linear. These will have the same time form. And this will oscillate between negative 0.1 amps and positive 0.1 amps. This will oscillate between positive 10 volts and down here where it is negative 10 volts. Okay? So with a resistor, we do still see an impedance. This is not an infinite current. There is a limit to how much current it is, and that limit is going to be V over R. Should write down here. V over R is our limit. Okay? This isn't going to be infinite. If we were to plug this into a DC circuit, we also wouldn't see an infinite. If we plug an inductor into the circuit, we will eventually see an infinite. If we plug a capacitor into the circuit, we see an infinite immediately. So it doesn't change a whole lot for resistors, but it does change a whole lot when it comes to capacitors and inductors. Let me draw an inductor now. We'll say this is now L, and this is going to be equal to maybe 200. Okay, we have the same VAC going into this component, but now instead of having this current value, instead of having 0.1 amps, what we will have is the relationship between voltage and current in an inductor is given by VL is equal to L DIL dt. So with this relationship, then what we have is, okay, IL is equal to 1 over L integral of VL dt. Well, what is the integral of, this is maybe, let's say 10 cosine of 5t, we'll say omega is 5. Just make the math nice. Oh, that's off the top of the screen. Need to learn my boundaries. 10 cosine 5t. Well, it's visible. Okay, then what we have for IL is IL is equal to 1/2 the integral of 10 cosine 5t dt. If we perform the integral of this, we get IL is equal to 1 over 2 times 10, because the 10 carries out, times 1 over 5, as we divide by, using the chain rule, times the integral of cosine is sine. We keep the same time form like this. Okay, this ends up being 1/2 times 1/5 times 10, which means IL is equal to 1 times sine of 5t. Okay, what does this mean? It means the maximum magnitude of our current is going to be 1 amp. And it's going to oscillate between 1 amp and negative 1 amp. And it starts as a sine curve. So here, this, like that. Pardon artistic phenomenality. I'm actually drawing this as an angle, and it looks way worse than video. That's fantastic. By the way, I am watching the comments, so if you want to ask a question, please feel free to. I do appreciate questions because I don't get to see everybody's faces, so I have no idea when you're dying on the inside listening to me. Unless you tell me, and then I do know. Just not. Well, I don't know. Maybe I don't believe you. All right. Well, so Walker just asked what's the circuit, so we're gonna start over from the beginning. Once upon a time, there was a force that was exerted on a wire that caused electrons to move. That force, you know what? I'll send you a Wikipedia article. I know a good guy who he can teach his stuff in the back alleyway. Totally violating coronavirus policy, but we won't talk about that. Somebody brought their sense of humor to class today. So calculating the current through components, what it really comes down to is figuring out what the voltage is across that component, and then being able to determine what the net response from the current is. Okay? So say I've got a system that looks like this. Okay? It's just a very simple VAC, RC, L components all in series. Okay? What we know is that KVL remains true, which means that VR plus VC plus VL is equal to VAC. That will always be true. KVL always is true. So, knowing this relationship, if we could figure out the distribution of how these voltages play out, we could figure out what the voltage is on each component, and from that we can figure out what the current is that's going through them. Okay? What we would do in our crazy world is we would say, okay, VR is equal to IR